Now you see, in continuation to our previous class, additional models we are discussing here. Two persons, A of mass 60 kg and B of mass 40 kg are standing on a horizontal platform of mass 50 kg. The platform is supported on wheels on a horizontal frictionless surface and is initially at rest. Consider the following situations. Already we have done this individually, but very good question. So we will discuss again. No issues. Both A and B jump from the platform simultaneously and in the same horizontal direction. This is also an irido model actually. Why I prefer this particular book is because he copied all the books. A jumps first into a horizontal direction, and after a few seconds, B also jumps in the same direction. See, in both the occasions, they will jump with respect to 3 meters per second. We will call this for a while as U. Okay. And masses are also different actually. Platform mass is also different. Now let us take the first case, question 6. In the first case, I will assume as if that you will have a plank whose mass is 50 kg and whose person mass is 60 plus 40, 100 kg. This is what we can consider because both are jumping simultaneously. So after jumping, before everything is rest. After jumping, the moment when it jumps, the person assume that he is having some velocity V1 and the plank thereafter will have velocity V2. So applying a law of conservation of a linear momentum, we have 50 times V2 is same as 100 times V1. Okay, this is 2 times V2 is 2 times. Remember, what is V1? What is V1? Velocity of the man with respect to platform is velocity of the man with respect to ground minus velocity of the platform. Correct or not? So actually they have given this as U, for example. And this is plus U. And this is plus V1 minus velocity of the platform backwards minus V2. So therefore, wherever I have V1, I can write V minus U2. So therefore, 2 times U minus V2. Right. Now I am going to use this stuff like this. This is a 3V2 is 2U. You have given U as a 3 meter per second. So V2 is 2 meter per second. What do you want? In this situation, just after A and B jump from the platform, velocity of center of mass of the system, there is no external force. Actually, I don't even require to do this, but velocity of center of mass is 0. Why? There is no external force. The velocity of center of mass of the system is 0. Why? There is no external force. If it is the velocity of center of mass of the plank, this is velocity of center of mass of plank. Remember, this is the case when See, this is equivalent to A plus B because both are jumping simultaneously. This is the case where both jump simultaneously. Final speed of the platform in the situation 1. In the first part of the question, you can see that both together are jumping. I think I have done the question also. No? Now you see, velocity of center of mass of the plank. Seventh question also I have done. Now again, we need to do the problem one after the other. You know, when jumping is happening one after the other, when jumping is happening one after the other, what happens? Now I'll take this as 50 plus. Who is jumping first? A jumps, right? So 50 plus 40. I'll take this as 50 plus 40. A 60 gada, B 40 gada. Once A jumps, B is still on the platform gada. Right? So now A jumps. Remember, he is A, who is 60 kg. Now he is jumping with velocity. Now I am straight away using, because I've derived here. He is jumping with a velocity u minus v2. And this system is moving back with velocity v2. Apply law of conservation of momentum. Even now also velocity of center of mass is 0 because no external force acts on the system. నేను బాగానే చెప్తా మార్క్స్ మీరు ఇంకెందుకు కన్వర్ట్ చేయటం ఇప్పుడు వాళ్ళు 40s 30s దాకా వెళ్ళినప్పుడు మీరు ఎందుకు పెరగటం లేదు ఎక్కడ ప్రాబ్లం వస్తుంది బాగానే చెప్తున్నాను నువ్వు చెప్పావు కదా బాగుంది నాకు అలా చిన్న చిన్న వాటికి సాటిస్ఫై కాకూడదు బాగుంది ముద్దుగా చెప్తున్నావు నేను తిట్టడానికి కూడా లేకుండా So this is the situation. So 90 times V2 is equal to 60 times U minus V2. This will become 150 V2 is equal to 60 times 3. 0, 0, 3, 5 times. So V2 is 6 by 5. This means 1.2 meter per second. Remember, this is the velocity of the platform. Velocity of a platform when only A jumps. Right. Next question. Next, the question is not completed. Now what happens next? Now what is your system? Platform plus B is your system. Now remember, platform, what is your initial system? Platform 50 kg, B 40 kg, and both are moving in this direction with 1.2 meter per second. Now this system, what is happening to this system now? Fifty kg, 50 kg Okay. A 1.2. This is 1.2. This is V. 2 now. Again. Right. Hold on. Hold on. And if this is a V2, this is always U minus a V2. This is 40 kg. Now you need to conserve linear momentum. So applying, don't you feel the entire chapter I have run with one single equation? Huh? You require any formulas for this? Right. That's how I deal with. Half para I have done full chapter. Applying law. మీకు ఐడియా వస్తుందా నేను ఈ స్టెప్ రాస్తున్నప్పుడు ఏది చేయాల్సి వస్తుందని? లీనియర్ మొమెంటం. LCLM అంటే లా ఆఫ్ కన్జర్వేషన్ ఆఫ్ లీనియర్ మొమెంటం. Minus 1.2 times 40 is equal to minus 50 V2 plus 40 times U minus V2. ఆగండి. This will become 12 for minus 48 is equal to minus 50 minus 40 minus 90 V2 plus 40 into U. U ante what do you mean by U? U is 3, right? So 90 V2 is 120 plus 48. Correct ena? Right. And that is 168. So what is V2 now? 168 by 90. Yeah, please tell me what is the value of this 168 by 90. I think I am getting a wrong answer actually. I am getting a wrong answer. I have done a mistake somewhere. Let me just correct. Excellent. Excellent. I have done one mistake here. You know what is the mistake that I have done here? Here, it should be 40 plus, no, it should be 40 plus 50. So here I went wrong. So the consequence is total steps are wrong. I went wrong, undoubtedly. I went wrong. Because I have considered mass of the system only the man. Actually, it is a full system. This is a full system. So therefore, 90 times 1.2, how it will become 9 times 12, or here 108, right? This is minus 108. This is equal to minus 90 V2 plus 42's 40 into 3, 120. Correct? So 90 V2 is 228. So V2 is 228 by 90. So what is a 228 by 90? 2.53. This is nearly 2.53 meter per second. But they have given the answer as anything mentioned. Nearly mentioned here nearly. So therefore, so you will get the answer as 2.53. Actually, if it is a 2.53, you should mark 2.53 only. Nearly mentioned. So decimal place, after decimal, there is only one place available. So for this purpose, 4 options, 2 point something, there is only one option. I marked that. Otherwise, if there is a 2.53, should mark 2.53 only. Any doubts? Boys and girls. Okay, it's a repeated model, practically speaking. Erido model also. Right. Please go through this question. Everyone, please go through this question. Yes. Now, please work on this question, everyone. According to, okay, I don't see all these things. Already this was done to you. Now what is happening? Two blocks of masses M and 2M are placed. Okay, fine. Spring is there. Okay, fine. Okay, kept touch. Okay, fine. A and B support. Okay, now M is moved towards the left so that the spring is compressed by distance x and the system is released from rest. Find the relative velocity of the blocks after M leaves contact with the spring. No issues. See, I see that in C frame of reference, initially, totally the energy is kinetic. Say, elastic potential energy. Agreed? By C frame. This is equal to half into small m into 2 small m by 3 small m into V relative square. Cancel, 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 cancel. V relative is equal to 3k by 2mx under root. Right. Any doubt? Therefore, the first part of the question is done. Array, same concept I am applying over the last 2 days. What to do? That is what we have for this week. Right. Now M arrives at B due to inertia of motion. M breaks the support B and due to some resistance offered by B, the resulting velocity of M is reduced to half of its previous value. Then what can you say about the velocity of 2M? See, please try to understand what is happening now. Remember, relative velocity is okay, fine. I know relative velocity is this. Let this be some, let this be some, we will call later, let this be some V naught for our convenience, only for our convenience. Only for our convenience. Convenience part. Right. Second part, what I personally believe is, now see what is happening now. Spring ko forget. Just forget about the spring. What is that you have is a block of mass 2m moving with velocity v1 and another block on the top, another block on the top which is moving with velocity v2. Small. This is where we are right now. Now, what you said, by the way, see, M arrives at B, at the end B, right? This is the state what I know. From this stage, you are reaching to which stage? Now you are reaching to a stage where V2 dash, V1 dash. Can I ask a question? For the whole system, is the momentum still conserved? Obviously, it's conserved. Now the issue is that, see, on small m, relative velocity is rightwards. Agreed? On small m, the relative velocity is rightwards. So therefore, friction acts in this direction. And this is kinetic friction. Whereas on the block, this is the relative motion direction. So friction acts in this direction. Okay. Now what happens when you are seeing a reduction in this? Obviously, here also you will see reduction. Yes or no? You will obviously see the same reduction. So what will happen now is that it will also reduce it to half of its previous value. How do I know? Friction is not there here, kada. 1 minute. Due to inertia of motion, M brakes support B, and due to some resistance offered by B, the resulting velocity of M is reduced to half of its previous value. So, there is no friction. Okay, right, right. I got the point. Now, what is happening is, I'll explain. You should consider this in a collision style, not in friction style. Because this end, whatever it is here, this will give some impulse. This end B gives some impulse. So as a result, what will happen is its velocity is reduced to V1 by 2 because of the impulse, because of the impulse given to here. Whereas on the block, if you notice on the plank actually, you will have the same impulse. So you said that minus G impulse is change in momentum. Agreed? So this is nothing but minus mv1 by 2. So wherever J is there, I can write mv1 by 2. And by the way, what is mv1? This is nothing but 2mv2. So what is impulse? mv2. Right. Now on this, if I apply the same impulse concept, initially you will have velocity v2. Because of the impulse, velocity might change. Velocity might change. So in this, because of impulse J on 2m plus J, because rightward direction we will always take positive, is minus mv 2mv final. This is the final momentum minus initial momentum v1. So J is nothing but minus 2mv final plus 2mv1. But what is J according to you? M, mv2. V2. What is J? mv2. So mv2 is minus 2mv final plus 2mv2. So minus mv2 is minus 2mv final. So therefore, V final is V2 by 2. Obviously, this is also becoming half. Yes or no? I'll start again. See, please try to understand in the course of its motion, actually till it reaches this what you call the boundary B, okay, continues with the speed V2 and this continues with speed V1 because there is no friction as per our question. Now what happens the moment when it reaches B, there is an impulse, means hitting is happening and this end, right end gives some impulse on the block leftwards. So as a result, the speed is reduced to half. As a result, speed is reduced to half. After impulse. Before impulse. Agreed? తేజస్విని అడుగు ఇక్కడ V2 ఓకే V1/2 ఎందుకు అయిపోయింది అదే కదా నీకు వస్తారు అదే ఎస్ V1 ఒక్క నిమిషం ఆగు నేను తప్పు చేశాను ఇక్కడ అబ్బా ఇక్కడి నుంచి అంతా కరెక్టే ఇక్కడి నుంచి అంతా కరెక్టే ఓకేనా రైట్ అమ్మాయి ఏంటంటే ఇందాక V2 రాశాను ఇది నేను తప్పు కదా ఇది V1 ఇది అప్పుడు ఇది V2 అని రాసుకోవాలి ఇది V2 అని రాసుకోవాలి ఓకే నౌ ఇట్ ఈస్ కరెక్ట్ ఎనీథింగ్ డౌట్ స్టిల్ ఆన్ దిస్ దరా క్లియర్ రైట్ ద లాస్ట్ మోడల్ in this. Now, after this, I'll give some theory again. According to the principle of conservation of linear momentum, if the external, see, in this particular question, I've done small mistake in writing the numbers. By the V1 rasa, ikkada V1/2. Initially, I've written V2 here. You written V1/2. That's the confusion for you. I'm just correcting this again. V1, V2. That's all. Okay. So before impulse V1, after impulse V1/2. So here also, what is this? Before impulse. So after impulse, I am assuming this is V final. Final velocity is Vf. So there I have proved Vf is V2/2, which means it is also reduced to half. What is the loss in energy of the system during the breaking up of B? What is the loss in energy of the system due to breaking of B? Okay. In fact, what is happening that I will explain now. Now, kinetic energy, no, I'm speaking about A right now. Kinetic energy, no, the top one, we will take it as A, B and different what I said. We will use a P and Q otherwise. Okay. For P, kinetic energy initially is half m V1 square. For P, kinetic energy finally is half m V1 square by 4. For Q, kinetic energy initially is half 2m V2 square. Kinetic energy finally is half 2m V2 square by 4. Right. So delta KE is KE initial minus KE final. Half m V1 square 3/4 times half m V1 square. Delta KE is KE initial minus KE final. This will also be 3/4 times half 2m V2 square. Any doubts? So now 1 minute. See whether you take 2m v1, 2m अरे మళ్ళా గొడవలు రాకుండా చూసుకుందాం 2m v2 or mv1, it is the same because the linear momentum is conserved. Let this be some p. Right. Now the question is the total. This is actually the loss. అంతే కదా. So total loss ఏమవుతుంది? Total loss is 3/4 common, half common. Now mv1 square I can write as p square by m. అంతేగా. Plus 3/4 into 1/2 into ఇక్కడ p square by 2m. సో 3/8 కామన్ తీస్తే 3/8 కూడా కాదు 3/16 కామన్ తీస్తే అంతేగా. ఏం మాట్లాడతా? ఎనీ డౌట్ స్టిల్ బాయ్స్ అండ్ గర్ల్స్? కదా క్లియరా? నాకు చెప్పండి ఒకసారి. మరి నేనేం చేయటం లేదురా మిమ్మల్ని. నీ డౌట్ ఏంటో చెప్పు నాకు. రే హాఫ్ mv1 స్క్వేర్ని హాఫ్ mv1 స్క్వేర్ బై m అని రాసుకుంటే దిస్ ఈస్ గోయింగ్ టు బి p స్క్వేర్ బై 2m. సిమిలర్లీ అప్లై ఫర్ ద లోవర్ వన్. ఓకే రైట్. ఇంకా ఏమైనా డౌట్ ఉంటే అడగచ్చు. రైట్. వాట్ ఈస్ దిస్ టోటల్లీ? 3/8 ప్లస్ 3/16 అంతేగా. అప్పుడు ఏం చేయాలి దీన్ని మొత్తం? హాఫ్ p స్క్వేర్ బై m కామన్ ఏమొస్తుంది మీకు ఇక్కడ? టోటల్గా ఏమొస్తుంది? 3/8, 3/16, 9/16. రైట్. ఇప్పుడు ఇక్కడ మీరు ఇనీషియల్గా తీసుకునే వి రిలేటివ్ వచ్చేసి v0. మీరు v1 ప్లస్ v2 పార్ట్ వచ్చేసి v0 అవుతుంది కదా. కరెక్టేనా? ఇప్పుడు మీరు v1ని ఏమని రాసుకోవచ్చు? దీన్నే ఏమని రాసుకోవచ్చు? v1ని p/m అని రాసుకోవచ్చు. v2ని ఏమని రాయొచ్చు? p/2m అని రాయొచ్చు. ఇది v0 మళ్ళీ అంతేగా. ఇది టోటల్గా ఏమవుతుంది? 3p/2mగా. హలో, ఇది టోటల్గా ఏమొస్తుంది? 3p/2m is equal to v0. అలా ఉన్నట్టు చెప్తాను. ఎక్కడైనా p/m కనిపిస్తే మనం pని ఇప్పుడు ఎలిమినేట్ చేసేయచ్చు నేను. అది నా ఉద్దేశం. సో ఇప్పుడు p స్క్వేర్ బై m కదా. ఇప్పుడు మనం p స్క్వేర్ అంటే ఏమని రాసుకోవచ్చు? 4 కలర్ చేంజ్ చేద్దాం. దిస్ ఈస్ 9/16 ఇంటూ p స్క్వేర్ అంటే 4/9 m స్క్వేర్ v0 స్క్వేర్ బై m వచ్చేసిందా? ఇప్పుడు మీకు v0 స్క్వేర్ అంటే ఏంటి? మళ్ళీ 9 క్యాన్సిల్. 1/16 m 1/4 అంతేగా. m v0 స్క్వేర్ అంటే స్క్వేర్ ఆఫ్ దిస్ టర్మ్. సో 3/2m x square. m cancel. So finally this is 3/8 kx square. So what is that they are offering us? 3/8 kx square. That is also there. Any doubt? Pakka? Sure? Right. So I have done the major problems. Now this is also there. Remember, n number of times you will get this question. You may get this question as multi-correct answer type, basically. According to principle of conservation of linear momentum, if the external force acting on the system is zero, what is happening? It means if the center of mass of the system is initially at rest, it will remain at rest. Right. Planck of mass m is placed on a smooth horizontal surface. Two light identical springs, each of stiffness constant K, are rigidly connected to struts at the end of the plank as shown. See, left one, right one will not move. Leftmost strut and is not but a solid fixing. Right. Okay. When the springs are in relaxed position, this is from here your actual question starts. The distance between their free ends is 3L. Okay. Block of mass M is placed on the plank and pressed against one of the springs so that it is compressed to L. So now this string is compressed. This is in compression state. To keep the block at rest, it is connected to strut by means of a light string, which means the entire string is initially at rest. Right. The system is in. Now the string is burned. The maximum displacement of the plank is. Please try to understand what exactly is happening over here. Remember, if we are compressing this by an amount L, okay, by the time it reaches here, it will get some KE part. Now remember, the block is not connected to the spring. The block is not connected to the, not fixed to the spring. Once the spring attains relaxed length, it is a free. Right. My question is, in the entire process, velocity of center of mass is 0. Agreed? Why? No external force. Now, if it moves, if the block moves, maximum it will move by 5L distance, not more than that. Yes or no? Now, if you imagine that the spring is the, if the lower block, because that this is moving, if the lower block, if lower block moves by X rightwards, or in other words, I'll use a different terminology for this otherwise. This is the relaxed stage. You compressed and released. It starts from rest actually. By the time the spring relax, this one will have velocity v1 and the lower object will have velocity v2. And the spring is relaxed. And thereafter what happens? Again, Now this is maximum compressor and it comes to instantaneous rest. Right or not? So in this process, with respect, yes or no, the system comes to instantaneous rest. Here also system is rest. So linear momentum also considered. So which I have clearly understood that with respect to Planck, maximum displacement of the block, will be 5L. Yes or no? With respect to Planck, maximum displacement is 5L. So therefore, displacement of the Planck is minus small m by small m plus capital M times displacement of the block with respect to Planck. By the way, have they given anything related to mass and all that? Yeah, small m, capital M, that's all. Minus small m by small m plus capital M times 5L. Minus sign indicates it is a leftward displacement. Minus sign indicates, no, 1 minute. It is minus 5L. Why? The block is moving leftwards. So finally, this is m into 5L divided by small m plus capital M. So you have option 2 matching for this. Any doubt? I'm still borrowing contents from the previous week only. But this you should understand. The stages you need to understand. Right. What is the maximum velocity of the Planck? That's fine. So whatever the energy stored, half kx max square is a half small m capital M by small m plus capital M V relative square. Okay, fine. One more. I know x max also. Half kl square is equal to half small m capital M by small m plus capital M. V relative means V1 plus V2 whole square. And by the way, one more important point is MV1 is same as MV2 according to law of conservation of linear momentum. So what do you want in the question? What do you want in the question? Maximum velocity of the plane. You want a V2. Eliminate V1 in this half small m capital M by small m plus capital M. In the place of V1, you can write capital M by small m plus 1 whole square V2 square. What do you want, by the way? Don't forget the maximum velocity of the plane. You want V2 actually. So this is half K L square. Cancel. And by the way, you can do one more thing here. You will get denominator m square, numerator capital M plus small m square. So by setting this properly, you will get m times capital M plus small m by small m into V2 square is KL square. So V2 is small m by capital M plus small m times anything doubt in this? The maximum velocity of the Planck. Am I right? Properly? Right. So, 16th question, they have given answer as a 3 and we got the C. The maximum kinetic energy of the block small m is half m V1 square. Once you have V2, you can find the V1. So from this, I'm changing the color. Changing the color by the way. So you want what? Half m V1 square. Half m. By the way, what is V1? V1 is capital M by small m V2 whole square. So this will become half m square by small m times V2 square. V2 square is KL square times small m by capital M plus small m into capital M. So this is half capital M by capital M plus small m into KL square. That is the kinetic energy. So this is the KE max of block during the motion. Any doubts? So with this, mostly I've covered all the models. Anything left? Oh, no issues. I'll complete it and I'll go for the next. Please tell me, have you understood this as a whole the question? Let me check whether I got correct or not. Half capital M by capital M plus small m. Half capital M by capital M plus small m. I should get the answer as 3 for this. Yes, they have given 3. Right. I got the same. Any doubts? Total question. Right. Next. Why don't you try this? Almost these models were done. Once these 2 questions are done, we are almost whatever that the questions that I planned for this week is done. Basic models. Wedge of mass capital M is placed on a smooth horizontal table. It has a curved smooth track from A to B. The track is shown like this, right? What do you want from this? A small block of mass M. Fine. Array, we have already done. We have already done this model. What is that? You are doing the problem in which frame? C frame. Can someone please tell me what is happening in C frame? Kinetic energy is 0 initially. Plus potential energy is mgh. Finally, you will have small m capital M by small m plus capital M V relative square plus potential energy is 0. Now I got V relative with this. V relative is capital M plus small m times 2gh by capital M under root. Don't forget V1 plus V2 is capital M plus small m by capital M times 2gh. Equation 1. Momentum is conserved. When small m have a velocity v1 in this direction, the wedge will have, whose mass is capital M, will have velocity v2. Only in this condition, you can apply law of conservation of linear momentum. When both the velocities are horizontal, only then you can apply law of conservation of linear momentum. Else you cannot conserve. Why? There will be a vertical component and mg acts. So you can conserve linear momentum all the time only along x-axis. So law of conservation of linear momentum implies mv2 is small m v1. Remember, only along x-axis. Equation 2. What do you want? V1, if height of A above, what do you want? It slides down with velocity V, right? V1 is what you need to find. Eliminate V2. V1 times 1 plus small m by capital M is, I think I've done this question actually, 2gh. So V1 is, so you multiply that. So what is happening is m by capital M plus small m times 2gh. Any doubts? So any problem till now, what I have done only 2 things. Conserved linear momentum Done the problem. Energy conservation is applied in sea freight. Right. Next. That is done. And this is the last question under this model. With this, I'll close. Go through this. Fixed wedge has a hemispherical. Okay, there. I actually collision concept is required for this. Okay. So now I'll teach collision theory. I'll teach collision theory now. Now I'll teach first one-dimensional head-on collision. So I'll do this part first. See, I am now discussing about something called collision. What happens in a collision? That's the first thing that we will study. For example, you see a situation like this. Let this be an object A moving with the speed u1. And let this be another object which is moving with velocity u2. The name of this is B. Suppose u1 is greater than u2. What happens? A will reach P. A collides P. Now what happens? After the collision, during the time of collision related to A will experience an impulse, an impulsive force, and similarly, the reaction of this B will experience an impulsive force. See, actually, I am not separating during the time of contact. During the time of contact. Remember, there are two stages involved during the time of contact. Now, till they attain common velocity. Okay? Earlier, please. Now, what is happening is u1 keeps reducing, u2 keeps, A speed will keeps reducing from u1, B speed will keeps increasing from u2. Somewhere you will see that they will attain common velocity. Till that stage, impulse is called, that impulse is called uh, im, impulse of deformation. That is called impulse of deformation. Whereas thereafter, whatever the impulse you see, that is called impulse of reformation. So you see two things here. Impulse of what do you call reformation, impulse of deformation. Here you are seeing deformation period. Right. Now similarly, till they attain common velocity, after they attain common velocity, just before they detach, that impulse is called impulse of reformation. It is impulse of reformation. Two things you will notice: impulse of deformation, impulse of reformation. And thereafter, what happens? A will move with velocity v1, and maybe B with, I'm just giving you an idea, B will move with velocity v2. See, remember, in all these situations, the center of mass of the system will lie, the center of mass of these spheres will lie on the same line. They will follow the same line pattern. Okay? They will follow the same pattern. Before and after, they lie on the same, the center of mass of the colliding objects will lie on the same line. Such a collision is called head-on collision. Okay, such a collision is called head-on collision. See, in this case, we will call this case similar as, what you will notice is, if during the collision, this is a contact point, right? This line is called line of impact. And this is also a common normal. Line of impact is a common normal. So, head-on collision, or see, in this, what is that you are noticing is, in this, what is that you are noticing is line joining center of mass of the bodies. Please remember, line joining center of mass of the bodies lie on the line of impact. In such collisions, and such a collision is also called as central impact. If this is not the case, that is called oblique impact, that comes under two-dimensional collision. So since I am dealing one-dimensional head-on collision, so what is happening, just I am clearly mentioning you. Also in this situation, if you plot a graph for any one body, if you plot a graph, taking the magnitude of as a function of time, you will see that the graph You will see the graph will have two regions. So this region which you are speaking about, yes, just reading this. Can see two regions here, two regions, obviously. This, in this region, they will, in the state of deformation. I can say that this is the period of deformation. And during this period, you will call period of reformation. Remember, I have drawn impulse on one of the blocks, so makes no difference. See, this you can clearly, you can understand this clearly by a simple example like this. Try to give you a simple example like this. A, and you have B, and you have some spring type of arrangement. Remember, as I mentioned, this is moving with the U1 and this is moving with the U2. After some time, what happens? A will come in contact with the B, not directly B, the left portion of the spring. Till that point, spring is relaxed. At some point of time, what will happen? Notice at some point of time, what will happen? The spring will be in the state of compression. So because of the compression, the spring will exert a force Fs in this direction on A and Fs in this direction on B. This is A, this is B. Now, can you please tell me what is the influence of Fs on A? Ah, yes, this will slow down U1. See, this Fs slow down A, and this Fs speed up B. How long? How long? So till both ends of the spring, here in this case, spring is maximum compressor. At that stage, both will have a common velocity. So till common velocity, compression takes place. Thereafter, what happens? No, the speed of B keeps increasing when compared over A, and with respect to A, the speed of B keeps increasing. So therefore, the spring starts recovering. Prior to this, speed is in the state of compression. After this, the spring will recover. So therefore, what happens thereafter, finally, at some point of time, you will notice that. At some point of time, you will notice that. This will have some v1 velocity, and totally detached from B, this will have some v2 velocity. Actually, this is what happens in a collision. Prior to this moment, spring keeps on compressing. After this moment, the spring starts recovering. So after this spring starts recovering. And thereafter, this is the velocity of A and this is the velocity of B. Remember, in the entire process, linear momentum, law of conservation of linear momentum is applicable because there is no external force. So therefore, M1 U1 plus M2 U2 is M1 V1 plus M2 V2. This you can apply. And on the basis of the nature of the collision, collisions are classified into three types. On the basis of any case, you can apply this. On the basis of nature of collision, collisions are basically classified into three types. One, this is defined as perfect elastic collision. Semi-elastic collision and perfect inelastic collision. In a perfect elastic collision, total Ke before collision is equal to total Ke after collision. There is no loss of K. Here, partial loss of Ke exists. And in this, maximum loss of Ke takes place. And after collision, both the bodies move together. So that is how they are classified. But this information is also not sufficient. For this purpose, Newton introduced a factor. Newton actually introduced a factor, and that factor is called, so definition, coefficient of restitution. This is introduced by Newton actually. Right. So what exactly the coefficient of restitution does? In fact, this is telling something about the degree of elasticity in a collision. So it measures degree of elasticity in a collision. Remember, it is a number and it's positive all the time. Right. So it is a ratio. How is this defined? It is represented with a letter called E, small e. So it is defined as impulse of reformation divided by impulse of deformation. In mathematical terminology, when the impulse stage is reforming, the force involved is Fr. You may ask me, how do I know this? In this graph, this area is nothing but Fr dt. And this area is nothing but Fd dt. Which means this area by this area is nothing but coefficient of restitution. Right. And that is one aspect. And another aspect is also there. So how do I know impulse of reformation or impulse? For example, you take A as one body. Initially, it is moving with velocity u1. Now, this is experiencing an impulse of deformation. As a result, it attained common velocity. You may ask me, what is common velocity? This is the expression for common velocity. How do I got this? Law of conservation of linear momentum. So now, as per Newton's second law, this is m1 vc minus m1 u1. Agreed? This is m1 times vc is m1 u1 plus m2 u2 by m1 plus m2 minus u1. And remember, this will become m1 times, you'll get m2 times u2 minus u1 divided by m1 plus m2, right? So actually, u1 is greater than u2, therefore jd can be written as m1 m2 by m1 plus m2 times u1 minus that's. Similarly, what is happening to A? Same A. When it attains a common velocity, then what happens? This will experience an impulse of reformation, after which its velocity becomes v1. Again, minus j reformation is m1 v1 minus m1 times v common. Don't forget, m1 plus m2 times v common can be written as m1 v1 plus m2 v2 according to law of conservation of linear momentum. Now you will substitute that here. You will get JR as m1 m2 by m1 plus m2 times v2 minus v1. After all calculations, you will get that. So therefore, what is, now why I am not doing all that? I have already done in the first case. So therefore, coefficient of restitution is reformation by deformation. Trust me, you will get V2 minus V1 by U1 minus U2. You know, what is this called V2 minus V1 in the present case which we are discussing? All this is applicable to this case. ఏదైనా డైరెక్షన్ మారితే దానికి మైనస్ చేయాలి మీరు ఫార్ములాలో. జనరల్ కేస్ హ్యావ్ డెరైవ్డ్. దిస్ ఈస్ కాల్డ్ నో. ఇంకా చెప్పాలి. ఇంకా ఏం చెప్తారు? చదువుకున్నారు మీరు. అంటే దాన్నే మీరు చెప్పేది కరెక్టే, రిలేటివ్ వెలాసిటీ. దానికి ఇంకా కంప్లీట్ స్టేట్మెంట్ ఇవ్వండి. జస్ట్ గివ్ మీ ది కంప్లీట్ స్టేట్మెంట్. రిలేటివ్ వెలాసిటీ ఆఫ్ సపరేషన్, relative velocity of separation, and this is along line of impact. Divided by relative velocity of approach along the line of impact. Now again I will classify. If E is equal to 1, it is called perfect elastic collision. So in this, Ke is conserved. Right. If E lies between, means it is not 0, not 1, somewhere in between. Such a collision is what we will call as actually inelastic collision is the general term. Inelastic collision or semi-elastic collision. Here in this, Ke is not conserved. E is equal to 0. This is called perfect inelastic collision. Plastic collision and kuda pilustaru, but I don't want to use that terminology here. In this case, Ke is not conserved. And one more important point is V2 is V1 in this case. So either they move together, or stick together. Both are possible. They may move together, same speed, or they stick together. Makes no difference. These are the observations. Any doubt? So I taught you everything at a fundamental level. Again, come back. I have started with what is the meaning of a collision. What is actually happening in a collision? Okay. They were moving with actually U1, U2 speeds. And while the process of colliding, one body will exert impulse on the other. As a result, there is a shape change in the border and deformation first takes place and thereafter reformation takes place. By the time total reformation is covered, they will separate with velocities V1 and V2. On the basis of this, you can do two things. During the time of collision, two set of impulses are noticed. One uh, the impulse of deformation and the impulse of reformation, right? The impulse which is acting during the time of deformation is impulse of deformation, and the other part is impulse of reformation, right? So what is actually happening in a one-dimensional head-on collision? You can see here, what is that you are observing in this particular case is that, see, you can see the bodies over here, A and B, for example, and their centers are here, and the line joining these centers is called a common normal. In fact, in this case, it is called a line of impact. All the velocities are along that direction only, before and after. Such a collision is called one-dimensional head-on collision. Here, in this case, the line joining centropass of the body lies on the line of impact. Such a case is also called as central impact. Now, if you observe what is happening with the impulse, the magnitude of impulse drawn along the y-axis, time along x-axis, you will see that this is some modal graph, not necessarily everything need to be the same. So I have noticed that, see, if you are hitting a ball with a bat, initially the ball will undergo a shape change maximum, and thereafter it will recover. This is the recovery region, and this is the deforming region. In this, what you will notice is, right, that is the stage. That I have explained with the spring situation. That I have explained with the spring situation. Right. Next, law of conservation of linear momentum, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. You can apply this irrespective of nature of the collision, because there is no external force. Momentum must conserve. Now, on the basis of the nature of the collision, you have observation. One is perfect elastic collision, the other is a semi-elastic collision, that is a perfect inelastic collision. In a perfect elastic collision, total kinetic energy before collision will be same as total kinetic energy after collision, and there is no loss of kinetic energy. Semi-elastic or inelastic collision. This is also called as inelastic collision, actually. There is a confusion always with that. That's the reason I did not return that time. See, when I said that it is inelastic, means not, I should refer perfectly inelastic. Even if it is elastic, I should say perfectly elastic. Right. So I have defined a coefficient, a number that gives you about the degree of elasticity in a condition. So this is all the things that I have done is a basic approach. In this, I have done totally one-dimensional only, strictly one-dimensional collision. Now you will have two-dimensional collisions also, which I will take up in the next class. Now continue just that. What if we are ahead of that? No issues. Right. Chalo. So from here I'll just stop. Yeah, 1 minute. You need to know one more fact. Final equations. Now, one thing is very clear. I have one relation. M1 V1 plus M2 V2 is M1 plus M2 times V common, which is M1 V1 plus M2 V2. This is on the basis of law of conservation of linear moment. And one more important point, V2 minus V1 is equal to E times u1 minus u2. Let this be equation 2. Now I am deriving final velocities in case of one-dimensional head-on collision. Right. Now what is happening here? Equation 1 plus m1 times equation 2. So what will happen? m1 minus v1. This term cancels. By doing which you will get m1 v2 plus m2 v2 is equal to either this will become u1 and u2 actually. I'll write properly. Yeah? If properly writing this, u2. Any doubts? No, you got finally v2. v2 is nothing but m1 times 1 plus eu1 by m1 plus m2. Similarly, you can write this is m1 because I multiplied with m1. That is v2. Similarly, you will have to take this part 1 minus otherwise. You will get the expression for v1. Okay. So by doing which you will get m1 plus m2 times v1 is equal to, okay, by doing which you will get m1 minus em2 times u1 plus m2 times 1 plus eu2 you take some equation here, equation 4, equation 3 otherwise. These are very standard equations. One more important time, don't derive. You need to remember this. For the entire chapter, I am asking you to remember only 2 equations. Right? That's all.